let's talk about graphing logarithmic functions. We are just going to look at the basics of log functions because this is a little bit challenging to do, not being together in the classroom. So what I want you to try to do is get feeling comfortable with understanding what a logarithmic graph would look like and sort of the properties of a log graph. The actual constructing of a graph, we're going to try a few basic ones, but it's just going to be for practice. Okay, so do your best with these, and of course email if you have any questions. So the parent graph of a log function is f of x, or y equals log of some base just of x. Notice we don't have any pluses, minuses, any stretches out front, any reflections. Okay, so here's our parent function. Now, what's really important for graphing is that we understand exponentials and logarithms are inverses of each other. Okay, so what we're going to do is we're going to use our conversion to exponential form to help us graph. So let's talk about a few characteristics. Exponential graphs had horizontal asymptotes. So since we're inverses, our log graphs are going to have vertical asymptotes. Remember, a vertical asymptote, a vertical line, will always be in the form of x equaling some constant. Okay, so this is a vertical line in which the graph approaches, but remember, never touches. Okay, the way we find it is by determining the horizontal shift. And just so you know, the parent function has the asymptote x equals 0. Okay? So our vertical asymptote is always in the form of x equals a constant. It's a vertical line in which the graph approaches, and it's found by determining the horizontal shift. The parent function has an asymptote of x equals 0. So with that being said, our domain for this is found based upon that horizontal shift and the vertical asymptote. Okay, for the parent graph, the domain is from 0 to infinity. So if we shift things to the right 2, now it'll be from 2 to infinity. Our range, the good news here for our range is going to be all real numbers, or negative infinity to positive infinity. Okay? So to graph, here's what you want to do, is you want to identify the parent function first. You are then going to convert the parent function to exponential form. From there, you are going to plug in 3 or 4 values in for y to determine x values. Then you're going to plot those and adjust if there are transformations. Okay, so let's look at this first one. This first one is a parent function. There are no transformations here, so that's good news. Now what we're going to do is we're going to convert that parent function to exponential form. Remember, our base is 3, so this is really saying 3 to the y power equals x. Now we're going to make a table of values, and as I wrote up here, we're going to plug in 3 or 4 values in for y to determine x values. Usually with my table, we plug in values for x and determine y. But notice, because we're talking inverses here, we're going to plug in for y instead of x. So I like to have at least a negative, 0, and a positive. And I usually plug in those 4 values. So what happens when I plug in a negative 1 here? I'll have 3 to the negative 1, which is 1/3. What happens if I plug in 0? 3 to the 0 power, anything to the 0 power, remember, is 1. How about 3 to the 1st power? 3 to the 1st is simply 3, and 3 squared will be 9. So now we're going to take those points and actually plot them. We don't have any transformations. If we did have a transformation, you would have to adjust these 4 points. So 1/3, -1, 1, 0, 3, 1, and 9, 2. Now notice, since there were no transformations and this is a parent function, that vertical asymptote for a parent function will always be at x equals 0. So my vertical asymptote is x equals 0. And I will sketch that in with sort of a dashed line here. Now I will connect the dots and make a curve. Remember, we never want to pass through that asymptote. So here is my log graph. Okay, and so that's what log graphs normally look like. Again, we could have them stretched if there is a dilation. It could be shifted to the left, shifted to the right, up or down, but this is the overall curve and shape of a logarithm. Let's check out what the domain would be in this case. Our domain is all our x values. So are all x values plotted? When we go to the left, there's a stopping point, that asymptote. So in this case, the furthest we go is 0. So my domain, and it's not included, is from 0. But this arrow here indicates we'll go to positive infinity. And my range, again, my arrow is going down. And here it is slowly but surely increasing forever. So my range is always all real numbers. Okay, let's look at one more example together. And that is the log base 3 of x plus 2 minus 1. Okay, so as you can see, this one has some transformations. Let's talk about those transformations. What would this plus 2 on the inside affecting x do? It would move it to the left 2 units, horizontal shift. How about the minus 1 at the end? That'll be a vertical shift. In this case, since it's subtraction, we'll go down 1. Now, when you have these transformations, we want to just think about the parent function to make life a little easier. So ignore all those transformations. We keep our base of 3, and we just have x. Now, we just plotted this graph, actually, on example 1. So you could literally take those points and then go ahead and do our transformation. So let's just review how we did that. We converted to log form, so 3 to the y equals x. Then we made our table, choosing values for y, and plugging them in to find x. Okay, but now recall, we don't want to plot these points. We need to take these points and use our transformations. So if I was to take the point of 1/3 -1, here that is, but I'm going to go to the left 2 units and then down 1. Let's take the point of 1, 0. Here is 1, 0, but I'm going to go to the left 2 units and down 1. Then we had the point 3, 1. but I'm going to go to the left 2 units and down 1. And last but not least, the point of 9, 2, but again, to the left 2 units and down 1. Now we want to connect that curve, but don't forget about that vertical asymptote. So as I had stated previously, our vertical asymptote is found by determining that horizontal shift. Well, we moved to the left 2. So that vertical asymptote is going to be x equals -2 since we moved to the left 2. And as you can see here, that is what we're approaching. So I will sketch that vertical asymptote. And now I'll connect the curve. Let's check out what our domain and range would be for this problem. So our domain, what is the furthest to the left I go? Well, that asymptote is stopping us at -2. So the furthest I'll go is to -2, but it's not included, so we use our parenthesis. And then what's the furthest to the right? Our x values are increasing to +infinity. And lastly, our range. Our range for all log functions is always all real numbers, and we can see that this arrow is going down forever for my y values and slightly increasing forever for my y values. So just recall, whenever you see transformations, first look at the parent function, convert to exponential form, choose values for y to plug in to find x. Then once you have those points, make sure to adjust the points based upon their transformations.